From the many craters of the moon's marred surface, to the strange, slanting rings surrounding the planet Uranus, our solar system bears the scars of impacts which echo its violent past. Over the last 4.5 billion years, the planets have spiralled, shuffled, and migrated between each other, intersecting one another's trajectories, and sometimes even colliding. In every region of our solar neighbourhood today, do we find evidence of cataclysmic impacts etched into the recipes of our neighbouring worlds. And in this video, we will explore this evidence as we journey back to a bygone age of intense violence around the young sun. Last time out, we talked about the history of Earth, but with one key detail omitted: the formation of the moon. And so perhaps that would be a good place for us to start as we revisit the many collisions of the early solar system. Before we dive into the collision that formed the moon, we first need to go back a little further, to a time before the terrestrial worlds we know so well today: Mercury, Venus, the Earth, and Mars. These 4 rocky planets are the product of more than 50 million years worth of catastrophic collisions between hundreds of smaller protoplanetary objects fused within the furnace that birthed the solar system. This close to the radiance of the infant sun, the only type of world-building material that could have existed would have been molecules of rock, with volatile substances like water vapour and ammonia forced outwards by solar wind. Therefore, once the accretion disk that formed the solar system had dissipated, the modern-day terrestrial neighbourhood was populated by more than 50 Moon to Mars-sized molten planetary embryos. And once accretion was no longer possible in the planet's forming process, collisions took over, as these embryos started careening around the inner solar system in highly eccentric elliptical orbits. Giant impacts between planetesimals ensued at an apocalyptic rate, as would-be planetary cores ploughed into one another and melted their rocky surfaces, causing them to coalesce into a single rounded body with a greater overall mass. After a few tens of millions of years of this chaotic cosmic dance, the majority of available rocky material had concentrated upon a handful of large terrestrial planets, among them the smouldering mound of radioactive rock that would go on to become the Earth. Within only about 20 million years of its formation, the young Earth had managed to accrue around 9/10 of its present-day mass. But it would soon encounter a bump in the road as another protoplanetary object came veering into its path, a Mars-sized body known as Theia, after the mother of Selene in Greek mythology, goddess of the moon. Theia, another body formed from the accumulation of rocky embryos, had its orbit around the young sun disrupted by gravitational influences from nearby planetesimals, causing it to deviate upwards and outwards from its conventional path. But as Theia resettled into alignment with the solar system's common plane, its trajectory intersected that of the Earth's. And around 4.5 billion years ago, Theia grazed our planet from an almost 45-degree angle, in the single most devastating blow the young Earth ever endured. The progenitor planet struck with such unimaginable force that it triggered a colossal, crushing explosion which obliterated Theia by shredding its outer layers, while blasting a huge hole in Earth's newly formed crust. Enormous chunks of rock were dislodged from both worlds and vaporized by the associated temperatures, casting a superheated cloud of mixed ejecta into orbit around the tarnished Earth. The debris within this diffuse ring then began to clump into larger aggregations away from the pressure of Earth's gravity. And within only a few hours, a single body started to dominate and sweep up the material that remained. And with that, Theia was reborn as Earth's only natural satellite, and by far the most complex satellite in the terrestrial neighbourhood, Luna, aka Earth's moon. And ever since, our moon has watched over the land as it has drifted ever further out into space, exerting gentle gravitational tugs on the planet, which drive a wide range of oceanic phenomena. This version of events is known as the Giant Impact Hypothesis, and it has been the mainstream scientific explanation for lunar origins since the early 1970s. Alternative theories, such as that the moon formed as a binary partner of Earth, or that it was captured from its formation around a gas giant, point to the fact that we don't see anything close to a satellite of the moon's complexity around one of the other terrestrials, despite all four worlds experiencing giant impacts at some stage. But none of these alternative frameworks are able to link so many of our planet and moon's fundamental properties like the Giant Impact Hypothesis, including the compositional similarities but not equalities of the two bodies, the apparent molten past of the moon's surface, and most of all, the angular momentum of the Earth-Moon system. The smoking gun piece of evidence for the Giant Impact Hypothesis is the axial tilt and speed of our planet's rotation. It spins on an axis with an obliquity of 23.4 degrees from the plane of its orbit around the Sun, implying that something sizable must have knocked the planet over in the past, while greatly increasing its rate of rotation. If it were not for this collision, a day on Earth in the present would last much longer than 24 hours, and without the resulting axial tilt it induced, there would be no seasons. As such, one has to wonder what life on this planet would look like if not for the collision that formed the moon. As it happens, longer days and the loss of seasonality are somewhat superficial when weighed against some of the other possible ramifications. If not for the Theia impact and the massive amounts of debris it brought with it, our world may not have been able to accrue that crucial final 10% of the mass we see today. And there's no telling just how differently things might have played out on this world with only a small tweak in its optimal mass, density and gravitation over 4.5 billion years. With less living space and lower tidal activity, life may have found it harder to wash out of the oceans, especially when making the jump to freshwater environments via lunar-induced estuaries. If nothing else, we can be certain that life would have needed to take a very different path of evolution without the moon by its side. A path which more than likely would not have arrived at human beings. All of this due to the Theia impact and the resulting moon it carved out. Giant impacts continued to rage across the solar system long after the moon had taken its place in the sky. In fact, for almost 500 million years after their formation, each of the terrestrial worlds was bombarded by large impacts which profoundly shaped their destinies. And while Earth ultimately benefited from its giant impact, another of its terrestrial siblings endured a much different fate: Mercury. This small yet fascinating world of extremes tells a sad story of a once promising proto-planet, which was pulverized by a series of colossal impacts that ultimately cast it into its tormentedly close orbit around the Sun. We know that the planet Mercury would not have formed this close to its parent star, as it would have been too hot in this vicinity to accrue a planet's worth of material, Moreover, Mercury's disproportionately oversized iron core, comprising some 85% of the planet's diameter, suggests it was once on a path to becoming much larger, perhaps destined to attain a size and distance comparable to the Earth. But before it could fulfill this promising potential, a giant impact drastically altered its fate, dislodging its entire mantle layer and sending the exposed core hurtling into its present-day orbit so close to the Sun. It certainly makes for a sad story, but only half of one, unfortunately, because attempts by scientists to simulate such a collision the way we did with the Theia impact often fail to deliver a world such as Mercury, especially with only one giant impact. A projectile would have needed to be the perfect size, arriving from an improbable angle, striking at a very specific speed, so as to strip the mantle layer without destroying the planet entirely. Furthermore, when NASA's MESSENGER probe arrived in orbit around Mercury in 2011, it detected traces of sodium and thorium, light elements we would expect to have been ejected by a particularly sizable impact. Therefore, contemporary explanations for Mercury's evolution lean more towards a series of successive collisions and impacts early in its life, which collectively degraded the rocky mantle. This scenario incorporates a number of smaller projectiles that struck with less force, which might explain why certain light elements were able to resist being ejected. But simulations have an even harder time making sense of this eventuality, with no clear consensus on the number or scale of impacts necessary. For example, a minimum of about 6 sizable collisions would have been needed to completely strip Mercury's mantle, if each arrived from different angles, whereas an unprecedented bombardment of up to 20 continuous impacts would be required if arriving from a single preferred direction. And either way, smaller collisions do little to explain how Mercury came to be booted from its original orbit to end up so close to the Sun. As it turns out, it is incredibly difficult to wind up with a world like Mercury in any eventuality. It is a true terrestrial oddity, both within our solar system and beyond. Our studies of over 5,000 exoplanets around other stars in the galaxy have found such small, super-dense rocky worlds like Mercury to be equally as rare this close to their parent star. There really is nothing else like it that we found. As such, the question of what happened to Mercury will remain one of the most intriguing terrestrial mysteries, and the truth is probably far more complicated than we yet realise. But Mercury's tale of torment was far from over, as the number of collisions plaguing the surfaces of the terrestrial planets remained stubbornly high, catalysed by the migration of one of our solar system's largest members, Neptune. Rather like Mercury, Neptune probably didn't form at the distance we see it today. There simply wouldn't have been enough stray planetesimals to facilitate the build-up of such a large world. Instead, we believe the planet Neptune began its formation around the same distance from the Sun as Jupiter. Beyond this point, it becomes cool enough for water vapour gas to settle and condense into solid ice, supplementing the growth of planetary cores with abundances of extra volatile material. As such, we believe that all 4 of the giant planets in the solar system formed around this boundary, known as the snow line, before migrating outwards to their more remote present-day positions. And around 4.1 billion years ago, as the young Neptune made its way towards the outer rims, its gravitational influence rippled a tidal wave of objects within the asteroid belt, the circumstellar fence of scattered rocks separating the gas giants from the terrestrials. This dislodged a swarm of rocky projectiles and sent them barreling through the inner solar system, pummeling the surfaces of the terrestrials for more than 300 million years. This seemingly unending age of chaos and torment is known as the Late Heavy Bombardment. And while each of the rocky planets weathered their own storm of projectiles, it was once again the young Mercury who suffered the most, bearing by far the biggest bruise from this age, the 1,500 km wide Caloris impact basin. It was carved out by a projectile at least 150 km wide, and struck with such force that it sent seismic shockwaves cascading through the crust right the way through to the antipodal point, squishing and sculpting Mercury's aptly named chaos terrain from the complete opposite side of the planet. The late heavy bombardment subsided around 3.8 billion years ago, as Neptune drifted far beyond the reach of the asteroid belt, into the shadowy recesses of the outer rims. And if we follow the giant into the darkness, we eventually arrive at the site of the next of the early solar system's great collisions, Uranus. Just as Mercury is an outlier among terrestrials, Uranus is a similarly ugly duckling amongst the giant planets, with a featureless surface that is often overlooked for the stunning tapestries of Jupiter and Saturn, or the extreme weather storms of Neptune. But Uranus's most striking characteristic is not immediately visible simply by studying its surface. For that, we need to look beyond the planet's atmosphere, where we find its chaotic collection of satellites and ring system propagating vertically over the planet. Uranus is the only planet in the solar system which spins on its side. Unlike the other worlds, which whiz around the sun like wonky teacups, Uranus rolls through space like a snooker ball, wheeling its rings, moons, and even its magnetic field along with it. Now remember earlier how we established that the Earth's 23.5-degree tilt is the result of an impact tipping the planet over? Well, Uranus's nearly perpendicular axial inclination is also thought to be the result of a collision. A much more significant collision in fact, with a considerably larger impactor than any we've discussed so far. As we mentioned, this far away from the sun's warmth, it becomes cold enough for volatile substances like water, ammonia, and methane to freeze solid and supplement the growth of planets. This would have resulted in generally larger, icy protoplanetary embryos than the warmer, predominantly rocky cores that proliferated the inner solar system. The largest of these ice worlds went on to grow into the cores of gas giants, while the less massive bodies continued to roam the outer solar system, eventually encountering the outwardly migrating ice giant worlds. And around 4 billion years ago, one of these renegade icy super-Earth cores, at least twice the mass of our world, rammed into Uranus, striking the giant planet in another grazing blow, and plunging into its atmosphere. This impact rolled the entire planet over on its side and supercharged its rate of rotation, shifting its momentum, gravitational influence, and even its magnetic field along with it. Unlike during the Theia impact, simulations of this collision show the progenitor super-Earth shattering inside Uranus's atmosphere, with the resulting debris largely absorbed rather than ejected. And this insertion of frictionally heated, volatile chunks that were unable to escape is what is thought to have shifted the planet's magnetic field according to this collision. Hardly any icy debris made it out into space, leaving virtually nothing for the formation of a giant impact moon like the one we see around the Earth. Instead, The only satellites emerging from this collision were tiny, asymmetric mounds of frozen volatiles, which barrel chaotically around the ice giant planet to this day, shepherding the material within its fine, dark system of 13 rocky rings. Far beyond the orbit of Uranus, on the very periphery of the planetary neighbourhood, we find our solar system's disowned member, the so-called dwarf planet Pluto. Pluto was once the well-established 9th planet in our solar system. By far the smallest and most remote world, its grainy, low-resolution images throughout the latter part of the 20th century concealed some of the solar system's best-kept secrets. But all that started to change in 2006, with the launch of NASA's dedicated mission to study the outer solar system, New Horizons. Its final objective being to capture detailed, close-up images of our 9th neighbour. But by the time it arrived, scientists had stopped referring to Pluto as a planet, following the discovery of a string of similarly sized mini ice worlds lying at similar distances, which threatened to overrun the classification of a planet. As such, later in 2006, members of the International Astronomical Union voted to amend the definition of a planet in a way that would exclude worlds like Pluto, Eris, Haumea, Makemake, and many others. Suddenly, in addition to being round and orbiting the Sun, a planet had to clear its orbital neighbourhood by slowly dispelling nearby non-orbiting objects, like asteroids, with the gradual whiplash effect of their gravity. Indeed, Pluto fails in this third criterion, unlike the 8 inner planets. Neither Pluto, nor any of the aforementioned trans-Neptunian objects, clear their orbital paths, as they all belong to the same circumstellar band of renegade icy planetesimals and dwarf planets known as the Kuiper Belt. This vast disk contains trillions of large objects, and probably hundreds of small, distant icy dwarf planets like Pluto. And in a neighbourhood so jam-packed with debris, collisions would have had an instrumental role in building up its most prominent objects. Pluto, in particular, bears the scars of a number of catastrophic impacts, which tell a story of carnage in the early Kuiper Belt. In fact, a number of Pluto's principal features are thought to be the result of bombardments, endured by the dwarf planet only shortly after it formed. And like the Earth, the earliest and most significant of these collisions, 4.5 billion years ago, is thought to have been the catalyst in forming Pluto's uniquely large moon, the celestial oddity that is Charon. Charon was discovered in 1978 when it became apparent that images of Pluto were being periodically elongated by a companion object, perhaps the most perplexing natural satellite we've ever found. At little under half the size of Pluto itself, Charon is by far the largest moon relative to its parent in the solar system. So much so that the centre of gravity shared by the two bodies actually lies just outside Pluto itself, leading some to view this system as a binary planet pairing. Regardless, these bodies are much too dissimilar to have formed as binary partners. Instead, Charon is thought to have been formed via a giant impact, like the one that kick-started the formation of Earth's moon, as a like-for-like dwarf planet grazed Pluto's newly formed surface, dislodging large chunks of moon-forming material from both worlds. Alternatively, Charon may have begun its journey in the Kuiper Belt, before becoming entangled by Pluto's gravity as it was captured. Both eventualities offer compelling explanations, but the picture was complicated in 2005 by the discovery of two additional tiny moons lurking beyond Pluto and Charon, named Nix and Hydra. And then moving into the following decade, as New Horizons made its approach, it uncovered another pair of even smaller moons, Kerberos and Styx. All four satellites lie well beyond the system's barycenter, and were initially thought to be leftover fragments from the collision that formed Charon. However, simulations struggle to recreate this scenario in practice. If the four smaller moons did indeed form at the same time as Charon, it's hard to see how they would have remained in orbit throughout all that chaos without being ejected by tidal influences. And so, scientists investigated the possibility of a second separate impact to kindle the four moons and keep them in orbit, perhaps a collision which grazed Charon itself. They determined that a 50-kilometre wide projectile from the Kuiper belt, around 1,000 times less massive than Pluto, would have needed to strike a sweet spot and dislodge about its own body weight in debris, which eventually concentrated into the four fragments. However, unlike the slowly evolving icy surface of Pluto, Charon's rocky surface is frozen in time, and should therefore preserve the scar of such an impact, in the form of a sizable basin that persists to this day. Alas, not even Charon's largest crater, the 240-kilometre wide Dorothy crater, is large enough to be attributable to such a collision. So perhaps the four satellites are indeed the result of a collision with Pluto. After all, New Horizons uncovered plenty of evidence for another gargantuan impact that tarnished the dwarf planet's surface, carving out perhaps its most enigmatic feature: its beating heart, the Tombaugh region. The Tombaugh region of Pluto is a giant, heart-shaped plain of nitrogen ice glaciers, by far the largest of its kind in the solar system. Its prominent western lobe, known as Sputnik Planitia, stretches for more than 1,000 kilometres, and is so bold and reflective that it stood out on grainy Hubble images of Pluto long before New Horizons made its approach. But during the famous 2015 flyby, we finally got our first detailed glimpse of this frozen nitrogen landscape, revealing jaw-dropping levels of surface activity and complexity, sparking frenzied speculation about what else may be lurking beneath the ice. Sputnik Planitia is thought to be situated atop a massive impact basin on Pluto's surface, formed around 4 billion years ago by a projectile at least 150 kilometres wide. It ploughed into the dwarf planet and carved an enormous 7-kilometre deep depression in its water ice crust, which soon started to act as a cold trap, accumulating a thick covering of volatiles which have since filled out the basin and frosted it with nitrogen ice. This surface nitrogen is so volatile that even the faintest rays from the 6 billion kilometre distant sun are enough to excite the material and cause it to sublimate into a gas, pumping gusts of nitrogen into Pluto's tenuous atmosphere. And so ironically, Pluto's icy heart really does beat on a daily basis, and this enables the circulation of gases which regulate its climate. But there's more to this beating heart than simply what's visible on its surface, because lying beneath the Sputnik Basin, multiple lines of evidence have converged on the existence of a subsurface liquid ocean of water. It might sound preposterous, the notion of water flowing on a world where even nitrogen freezes solid, but the presence of a buried slab of liquid water, together with some kind of anti-freezing agent like ammonia, would explain a number of the Tombaugh region's most peculiar properties. starting with its curious orientation relative to the moon of Charon. Sputnik Planitia happens to lie on almost the exact opposite side of the dwarf planet to the one that is tidally locked in synchronous rotation with its moon. But the chances of the basin actually forming in this spot are considerably low. What is more likely is that the impact occurred closer to Pluto's north pole, but the dwarf planet has since readjusted itself in line with its revised distribution of mass. This phenomenon is known as true polar wander. It is the tendency of planets and moons to reorient themselves with respect to their axes, so that large volumes of mass may be distributed along the equator, while areas of underdensity shift towards the poles. In simple terms, when this impact grazed Pluto's surface, the infilling of dense ices in the resulting basin became so massive that it dragged Pluto's entire crust as it shifted towards the equator. But this mixture of nitrogen and methane ice would not have been sufficient to drive Pluto's wandering heart by itself. There must be something even heavier lending a hand from further down. And that something is thought to be an elliptical upwelling in the subsurface ocean, which has seeped into the part of Pluto's crust that was thinned out by the impact. Both factors combined to create a positive gravitational anomaly, which caused Pluto's crust to slide atop its ocean into its present configuration. The question is, how has this ocean managed to stay liquid on such a cold body after so many billions of years? The answer, once again, is Pluto's moon of Charon. As it orbits the dwarf planet, its reciprocal gravitational influence gently tugs and squeezes Pluto's interior, creating a source of friction within the mantle layer, with the resulting tidal heat allowing the subsurface ocean to stay warm enough to persist in a liquid form. As heated material bubbles up towards the surface, it presses against the cold underside of the icy sheet and refreezes, causing it to expand and create faults in the Sputnik plane. And imprinted all over the images snapped by New Horizons, we do indeed see what appear to be convection cells in the ice, providing yet more evidence for the existence of this underground ocean. The presence of such an ocean hiding out on Pluto, even if not a particularly warm or viscous one, would have seismic implications on considerations of life beyond the Earth, by broadening the cohort of potentially habitable worlds to encompass distant Kuiper Belt objects. And in the case of our favourite dwarf planet, none of this complexity would have been achieved without the many collisions that battered Pluto early in its life. As violent and unpredictable as this age of the solar system clearly was, it was also an age of creation and design, as new stories were kick-started right across the solar neighbourhood. Perhaps without the Theia impact and the resulting moon it dug out, the prerequisites for an eventual awakening of life on this planet may not have been met, and one can easily imagine the implications that would have. If nothing else, we can at least be grateful that the solar system got this early age of violence out of the way before the emergence of life, or else we would never have a chance. And with that, I bid you good night. C signing out.